This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. CARTA brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
So I'm going to change gears a little bit and talk a little bit more about behavior and selective forces acting on sort of larger behavioral packages. But I have to say I do so with a certain degree of anxiety because, thanks to Photoshop, because there's two reasons really why this talk has given me enormous attack of the nerves. One is that as you've already learned, this is a really confusing topic, and anybody who ventures to say they understand how our genus arose is probably self-delusional. But the other problem is that I actually started my career actually getting interested in studying the origins of Homo, and so I have some kind of psychological issues that I have to work out. And so I hope you'll forgive me if I start off this lecture a little bit autobiographical. And I'll tell you a little bit how I got interested in this crazy problem, which is that when I was a freshman in college, I actually started working on this fossil to try to estimate its cranial capacity. And I thought that was really cool, and we published a paper, and wow, that's what I'm going to do for the rest of my life. And then because of that, for my senior honors thesis, we did the first probabilistic study to ask if Homo habilis and this thing, rudolfensis, were different, and that was really fun. And then, of course, the next question, which was really the subject of my master's thesis, was to see if we could figure out the evolutionary relationships among these things. And my conclusion was there's so much convergence, what we call homoplasy, that it was a completely impossible task. And so I gave up on all this sort of stuff and got involved in working on other things like the fossil record and doing biomechanics and stuff like that. But all along, I've been really interested in the origins of Homo. And one problem that continually puzzled me is that basically I'm a splitter, right? If I can split species, I generally prefer to do that rather than being a lumper. But I'm convinced that the species Homo erectus really is a bona fide species, and it's lasted a long time. And it's had an enormous range of variation. It's actually more or less doubled its brain size over the course of about 2 million years. And there seems to be sort of this gradual increase in brain size, regardless of what the errors might be for some of those points. And furthermore, as we're going to learn a little bit later on, there's also an enormous amount of variation, not just in brain size, but also in body size in the species. And as you'll learn from Leslie Ayala, who will be talking later on, and also from Herman Ponzer, who will be talking later on, there's an interesting energetic issue here, because bigger brains and bigger bodies, and there are probably other shifts going on, like in life history, require extra energy. And these are some estimates that Leslie Ayala and Kathy Key published a bunch of years ago. It's one of my favorite papers. And they more or less estimated that Australopithecus, a female like Lucy, she would have needed about 1,200 calories a day more if she were lactating, whereas a female Homo erectus would need a good 50% more calories per day. And again, that amounts to quite a number of calories that are required if they are lactating. So, and at the same time, more energy is needed. You also see that Homo erectus has smaller teeth. So this is tooth size of Homo erectus compared to Homo habilis and Australopithecus. And at the same time, also, these are estimates of bite force from a paper we published a few years ago, showing that the genus Homo is able to produce much lower bite forces than those of Australopithecus. So therefore, if they're getting more energy, it's not from eating more food, it's eating from higher quality food. So this raises two interesting questions. So one is, how did early Homo, and I'm going to focus primarily on Homo erectus because I don't really know how to make sense of the earlier stuff. How did it get more energy? And secondly, what was the effect of more energy on our early Homo erectus evolution? And again, I'm going to focus on Homo erectus. And so there are a lot of hypotheses out there. People have been thinking about this for a long time. One idea is that it has to do with food processing, better efficiency at long-distance locomotion. You might call that trekking. I've been, of course, very obsessed with the idea of running and its importance in hunting, and I'll talk about that in a second. Origins of meat eating, food sharing, extractive foraging, the list goes on. And to me, when you actually look at all these tasks and put them together, what they suggest is that actually what we're looking at is the origins of a way of life that still exists, just barely, called hunting and gathering. And to me, hunting and gathering is really an integrated system. There's no one component to it. It's not just hunting and gathering, although those are both important. So you have meat is an important component of the hunting and gathering diet, either through hunting and scavenging. There's also foraging, but importantly, it's often extractive. So you're actually digging things up rather than just plucking them off trees or collecting honey or whatever, things that take more effort. But you can't make the system work without also without tools and food processing, and I'll talk about that in a second. And furthermore, the system also requires intense cooperation in various ways, division of labor, food sharing, and so on. So I would like to suggest that actually much of what we think about in terms of the origins of Homo has to do with this hunting and gathering system, and that you can think about it as a trend, not as a moment in time when, voila, the world's changed, and as a trend, a selective trend that has a lot to do with energy, and that you have selection for two major kinds of skills. First of all, there are the cognitive social skills, the skills that require increased intelligence or brains. That's very important for being a hunter-gatherer. But there are also athletic skills. Hunter-gatherers are athletes. They actually have to go out and do work every day and use their bodies in complex ways. And a lot of the athletic activities that hunter-gatherers do involve endurance athleticism rather than power or speed athleticism. And those in turn led to increased energy availability, which then permitted selection. You might say it released selection, released constraints on selection for bigger brains, et cetera, that drove the system forward. Here's a more formal version of the model. So you have selection for better hunting and gathering abilities, a combination of brains and brawn, not just brains over brawn. This leads to increased available energy, and of course, that's going to be especially important for mothers. You can only do so much with energy. You can either increase the use of energy in reproduction, or you can increase it in maintenance and growth or somatic investment. And that will lead to not only maybe population growth, but also energy that can grow bigger brains, grow bigger bodies, have longer life histories. And that indeed leads to selection for athletic, better athletic capabilities and better cognitive capabilities, which then keep the system going forward. And so that you have what I would call a sort of classic feedback model. Now, in only 18 minutes, I don't have the opportunity to go into great detail, so I'm going to focus on just a few aspects of this model, and I'm going to focus in particular on hunting and scavenging, and then briefly talk a little bit about food processing. So I've been interested for many years about the problem of how it is that early hominins hunted and scavenged. So here we have Usain Bolt mythically racing a cheetah. It would be no contest because Usain Bolt is the fastest guy on the planet, but he can run about 10 meters a second, can do so for about 10 or 20 seconds. Pretty much any quadruped out there on the savannah can run twice as fast as Bolt and can do so for about 4 or 5 minutes. So he would have no chance being either prey or, for that matter, escaping from any predator. In addition, hunting is difficult and chancy. Humans lack natural defenses, and also until very recently, we lacked any kind of technology. This is the oldest known stone point. It's controversially dated to 500,000 years ago from southern Africa, and actually really stone points really don't appear commonly in the archaeological record until about 300,000 years ago. So that means early Homo, if it was hunting and scavenging, did so basically with just a sharpened wooden stick or some rocks to throw. And then finally, if you're going to become a carnivore, you also have to deal with other carnivores, and that's a very dangerous guild to deal with. I wouldn't like to do that. I certainly, when these things happen, I stay in the Jeep. I don't get out of it. So Dennis Bramble and I at the University of Utah, based on earlier work done by Dave Carrier, have argued that one important factor that helped early hominins become hunters, after all, it's kind of a weird thing to think about bipedal primates becoming hunters, is our incredible ability to run long distances at relatively fast speeds, endurance running. And I don't have time now to go through this list of wonderful features that we all have in our bodies, literally from our heads to our toes, but we have a wide range of adaptive features, features that improve our performance and our ability to run long distances. Even if you don't run long distances, you have the ability to do it. In fact, you're right now sitting on one of those features, your gluteus maximus. It's especially enlarged in humans, and we think there's good evidence that it's an adaptation for long-distance running. And some of these features, of course, we can see in the fossil record. Some of them we can't see, of course, because they don't preserve. We also have some of these features, and the features I've listed, with the exception of long legs, I believe can really only make sense in terms of their ability to improve in performance in running, not walking. So these are not just consequences of walking a lot. These are features for running. And also intriguingly, and again, I don't have the time to do this today, a lot of these features, not all of them, first appear in the genus Homo. Some of them appear in Australopiths, that's for sure. Some of them we can't see in early Homo, although we have some guesses about them from footprints that are dated to the same time period. But for the most part, if you look at the package of features that make human beings able to run marathons or other sort of long-distance events, they more or less appear in the genus Homo, and I think that we can say that with some degree of confidence. So how would these have been adaptive? So one hypothesis is that may have been important for the very earliest meat eating is that we started off, or our ancestors started off scavenging. This is called power scavenging, where you detect a scavenging opportunity, and one way to do it would be to observe vultures in the distance. And in fact, there's some really neat data from South Africa showing that actually vultures do this to do this. So vultures follow other vultures, so why couldn't hominins do this too? And if you do this in the middle of the day when we can run better than other animals, you would, particularly other carnivores, you might have an opportunity to get to these carcasses before, say, the hyenas or other competitors could have gotten there. And so that might have been an advantage. We think that the really more important process that maybe happened later, because we have evidence that hominins are hunting. They're actually hunting large adult prime males by at least 2 million years ago, is a mode of hunting that still exists. It's kind of rare, called persistence hunting. And it's been documented all around the world, in Africa, in the New World, in Asia, in Europe, etc. But of course, it's become less common today because we have not only supermarkets, but also bow and arrow and dogs and nets and things like that. But here's how persistence hunting works. The first thing, so I've graphed here on the x-axis speed in meters per second, and in blue here I've got the endurance running range for human beings, and here's our sprinting range. And here I've got the trot range for various quadrupeds. So humans can run marathons, for example, well above the trot-gallop transition speed of dogs the same size as humans, well above ponies, and actually good human runners can run above the trot-gallop transition speed of horses. So we can run long distances at speeds that make quadrupeds gallop. And importantly, when we run, we cool primarily by sweating, such as this woman at the Westminster Dog Show. But where her dog and this zebra, for example, that's being chased, or by a film crew, obviously, can't sweat. They don't sweat, but they cool down by panting, short, shallow breaths. And the cool thing is that when animals gallop, they cease to be able to pant. That's basically because their guts slam into their diaphragm with each stride, and so that's a serious constraint. So if you go on a hot day, don't take your dog for a really long run and force it to gallop, you'll kill your dog. So that enables us to do something called persistence hunting again. As I said, it happens in the heat, so people typically do it in the middle of the day when it's really hot. They'll pick really big animals. The bigger the animal, the better, because big things overheat faster than small things. And they'll chase that animal, force that animal to gallop. Of course, the animal will gallop faster than the human can run. The animal will hide in the bushes, but then the human chases it, tracks it, usually at a walk, finds it again, and then chases it again. And so there's this kind of dance. In fact, it's called in South Africa by the Bushmen sometimes the Great Dance, in which they go from the chase versus track, run versus walk. And over the course of about 15 to 30 kilometers, again, only about half of that spent running, they can drive animals such as this kudu into a state of hyperthermia where the animal's going to die anyway. And according to the number of hunts that have been followed by Louis Lieberman down in South Africa, about 75% of the hunts that he's followed, these persistence hunts, were actually successful, which is a remarkable level for hunting. Now, of course, hunting is not all about running. There are many other adaptations which I think are very important. For example, we've done work in my lab on throwing. Obviously, you need to walk long distances in order to run. You have to carry food back. You have to carry weapons or things to defend you. The ability to lose heat is very important. And I would also argue there are important cognitive adaptations which are important for hunting. For example, you have to be able to track an animal, which is not a trivial task. You have to have really good spatial memory and mapping. You have to have a good theory of mind. There's this wonderful book by Lieberman, actually, in which he goes through the various kinds of cognitive tasks that are necessary to do this kind of hunting. You have to be a really good naturalist with knowledge of the ecology. You have to have sharing and division of labor and communication, etc. So I'm not arguing that hunting is the sole deal here. And furthermore, I would also not make the argument that these are features that only were beneficial for hunting. Obviously, some of these features would have been important for example, getting honey, for digging underground storage organs, and so on. So there's a lot going on. I've just been focusing on hunting. I don't want to overstate my case here. But I would also argue that, again, there's more, right? Again, there's a lot of systems here to talk about, and I just want to talk about one more of them today, because, again, we don't have time to do everything, and talk about the importance of, I would say, is food processing. So let's imagine you're a hunter, and you've come back from a long day's hunt, and maybe one of those 25% of the time, or maybe even more, who knows, that you came back empty-handed. So you've been gone for much of the day chasing some kudu, and damn, you didn't get it. You didn't get a lot of food. You come back and you're hungry and you need food, right? You don't want to go into negative energy balance. Now, unfortunately, I would say 2 million years ago, cooking hasn't yet been invented. In addition, if you try to eat the normal kinds of foods that foragers eat, you're going to have to spend a lot of time doing it. Food processing, chimpanzees spend about half their day eating. They fill their bellies, wait for their bellies to empty, fill their bellies again, wait for their bellies to empty. Do that. Basically, that's what they do all day long. You can't afford to spend all night long eating, waiting for your belly to empty, to fill it up again, to go the next day. And then finally, if I were to give you raw meat to chew, which of course doesn't require that much time to chew, you'd actually have a pretty horrible time doing it. You should, by the way, check out this video. This is a piece of goat that we gave to somebody in our lab, and after raw goat, I should say, and after 40 chews, you can see these are the other particles. We had the person spit it out, and you can see that after 40 chews, this person was unable to actually reduce this particle any smaller. In fact, and you can also try this experiment at home if you'd like to. The point is that human teeth are dreadfully designed or adapted for chewing raw meat. But there's a simple solution. All you need to do is the sort of simple processing that was invented back in the Oldowan that might have been, started around 3.3 million years ago. You can cut your meat, which of course people still do today, and you can also pound your underground storage organs and break them into smaller pieces. So again, I would argue that this suggests there's some kind of feedback loop going on in the genus Homo, right? You've got selection for better hunting-gathering abilities. That's not just brains, but also brawn. And I would argue that many of these athletic capabilities have to do with endurance, but not all of them. Power is important sometimes. And that we have, again, this feedback loop, giving us more energy, allowing more more investment, not only in reproduction, but in bodies, which then improve capabilities that provide extra energy, which drive this loop forward. And of course, for a theory to be useful, it has to have some predictive power, and I would say that it helps us explain several trends that we see in the genus Homo. So one, for example, is the dispersal of humans out of Africa. If you do some basic models, I'm not going to go through the math now, if you have early Homo increasing its population size by 0.4% per year, which is about average for many hunter-gatherers today, and you keep group size and population density about the same as hunter-gatherers, you can actually account for the dispersal of hominins from Nairobi all the way to Tbilisi in between 50 and 100,000 years. Secondly, I would argue that all this increased energy might have been just what was necessary for that increase in brain size and also body size that we've observed and already discussed about in the genus Homo. It also, I think, explains an interesting specimen, Homo floresiensis, because we've talked about increased energy driving this positive feedback loop in Homo. Well, what happens to those poor descendants of maybe Homo erectus that ended up on the island of Flores? Then they're stuck there, and there's not much food. And it seems that their selection drove them in reverse. So they went down to smaller bodies, and their brain sizes shrunk even more, presumably as adaptations to save energy. And then finally, I think also it helps us explain why we have such a hard time not only talking about the origins of the genus Homo, but also its next transition to archaic Homo. Another maybe not so well kept secret is we have a hard time defining Homo heidelbergensis just as much as we have defining Homo habilis or Homo erectus. And this is an analysis I did a few years ago, but if you take this fossil, which is an early Homo erectus, and blow it up to this fossil and actually look at the differences in size and shape, actually you hold size constant, basically Homo heidelbergensis, this archaic Homo, is a version of Homo erectus that has essentially a bigger brain, you can see that from these arrows, and a relatively larger face, which I would argue scales with having a bigger body. So basically, I would argue that archaic Homo is a Homo erectus that's basically had its brain blown up and its face and body blown up, and that's more or less what you get. And there's plenty of evidence now that it's maybe then an archaic Homo, and I hope Leslie Ayala will agree with me, that it's really an archaic Homo that we see this slowdown in life history, this extended period of childhood, because early Homo erectus doesn't have that. And I would venture to guess, though we don't have any evidence, that if you found an archaic Homo, it would have lots of body fat like most of us today, but not like chimpanzees. I don't mean excess body fat. I mean, the thin humans are still fat compared to most primates. So in short, hunting and gathering, I would argue, favored selection for both brains and brawn, and in particular, I would say endurance athleticism, and that more brains and more brawn led to increased energy availability, which released constraints on selection for yet more brains and brawn, and drove an interesting feedback loop. And the ramifications of this are particularly interesting in a world today where we get all the energy we want from the supermarket and no longer have to do any endurance athleticism in order to get it, but that's obviously another lecture. Thank you.